Okay, here look at another problem where let's say we have half a ring, or you could say half a circle, basically a semicircular piece of a wire or a charged wire. And if you think about this, this is just like a straight wire, only we bent this into half a circle. So this can still be described by our usual one-dimensional intensive property of charge per unit length, or in this case charge over half a circumference, which is pi r. Likewise, if we just consider perhaps a infinitesimal amount of charge, dq, we see that the electric field at the center over here, or let's say downwards here, is going to be dE. Okay, so that's pretty much it. Now we say this is going to be dq over dl across that small length of our wire. So that's how we can define that intensive property for this. Okay, but now what about our electric field for this guy? Well, let's consider two parts of this. Let's consider at one extreme, there's some dq here. And that's gonna have an electric field that goes this way. Then we consider a part just like it on the opposite end of this symmetrical semicircle, has an electric field that goes this way. So now again we have that same scenario we had before. Remember that these are described by vector quantities, so we gotta break them down into their x and y components. So we see that is going to be dex, and that will be dey, and that is under the context we treat the center of the semicircular ring as our origin, as such. And my battery's dying again. So now continuing with this a bit at a quicker pace, we see there's dex and there's also dey here. And now from this, it's plainly evident that our x components are going to cancel out. Meanwhile, our y components are going to add up to each other. Okay, so now we know that we need only worry about the y components for our electric field. So let's go ahead and set this up. And we'll do that in a coming video. I need to charge this battery, not enough juice.